I guess it is started.
It is started. It is started. Thank you. Thank you so much. Okay, so let me start the presentation. Uh, but before the presentation, I wanted to apologize all the students. This week was really painful for me, running around from home to hospital and hospital to home. But finally, now we are okay. So sorry for any inconvenience caused to any of you. As promised, there will not be change in any of the weightage of the examination. We will have all three examinations done, but it might require us to do some extra classes, and there I sincerely look for the cooperation from your side. I'm really sorry to ask this, but I hope you all will help me in this. Okay, so let me just start the presentation. Is it visible to everyone? Slides are visible to everyone?
Yes, sir.
Okay. Okay, so till the last class we started looking at the concept of a gray body. We said that, so see, we started in this chapter, we started with the black body, saying that the black body has everything perfect. It has emissivity equals to 1, absorptivity equals to 1, there is no reflectivity, and it behaves ideally, isn't it? So all the laws which we have seen, like uh, Planck's law or Wein's law or Stephen Boltzmann law, these are for the ideal bodies, isn't it? So these are for ideal bodies. That means these are only for a black bodies, isn't it? But when we are looking at the real life systems, so real life systems do not behave like a black body, isn't it? So you can see that in a real life system we will have a absorptivity and emissivity lower than the 1, isn't it? So in between these real bodies and the black bodies, there is a gray body. So these gray bodies, basically these gray bodies do not have the emissivity and absorptivity equals to 1, but they more or less behave like a black body. So when I'm saying they behave like a black body, what I mean by that is you will see that the absorptivity and emissivity are independent of the wavelength. That is the most important part. Okay, so how to deal with the gray bodies, that we started looking at in the last class, and the rationale behind saying that is the real bodies are more or less close to the gray bodies. Instead of saying that the real bodies are close to the black bodies, we should say that these are more close to the gray bodies. Okay, so in addition to the usual concept of emissive power and intensity, etc., there are some more additional concepts comes into the picture, isn't it? And these we have defined, isn't it? So we have defined irradiation. So irradiation is nothing but total radiation that hits the surface per unit area per unit time. It is denoted by Z. And there is another term which is defined in the last class, radiosity. So radiosity is nothing but total radiation that leaves a surface per unit area per unit time, and it is denoted by J. So you can see that if you are talking about the black body, radiosity is same as emissive power in case of black body, but in a gray body both are different, because in a gray body the radiation leaving the surface, these have two components. One will be the emission and another component will be the reflection, and therefore the radiosity for the real bodies or a gray bodies are different compared to the black body. That is what we have seen in the last class, isn't it? Based on that, we try to correlate what will be the heat loss or a radiation loss from the gray body. That is what we try to correlate, isn't it? So we said that uh, the emission from a gray body, emission from the gray body will be what? emissivity multiplied by emissive power of a black body, isn't it? If the temperature is same, whatever the emission I am going to have with a temperature T for a black body, if I multiply that to a emissivity of a particular body, I will get a emissive power of a gray body, isn't it? Also, in addition to the emission, there will be a reflection. So reflection will be what? Whatever the incident radiation is there on the gray body, how much of that is getting reflected? So that will be given by what? Reflectivity multiplied by the incident radiation. Incident radiation we are accounting through what? Irradiation. So rho into G gives me the amount of energy will be reflected from the gray body, and sum of both these will be what? Sum of both these will be radiosity. So J is given by E epsilon B plus rho G. That's what we have seen in the last class. Again, rho. So if we are assuming that a gray body is there is no okay, so there is no transmission in the gray body. So remember, transmission takes place only in the opaque surface, isn't it? So there is no transmission there. So transmissivity tau is 0. In that case, what we can say is, remember, alpha plus rho in plus tau equals to 1, and since tau is 0 here, alpha plus rho equals to 1. So I can find out rho as 1 minus alpha, and then again from Kirchhoff's law, 1 minus alpha can be given as 1 minus epsilon, isn't it? So this 1 minus epsilon, if I put it here in place of rho, what I get is radiosity comes out to be E epsilon B plus 1 minus epsilon G. Now net heat loss from the surface A will be given by what? Net heat loss from the surface will be whatever the radiosity I am having minus the radiosity is the total energy going out from the surface, isn't it? But at the same time, some energy is coming to the surface in terms of irradiation. So subtraction of these will be the net loss from the surface, isn't it? So that's what we have written here. Q by A is a net loss per unit area from the surface given by what? It is given by radiosity multiplied by radiosity minus irradiation, isn't it? So J minus G gives me the net loss from the surface. So I can put all terms here. So J we have already opted here, so that we can put here minus G. So we get E epsilon B minus EZ. Again, this G we can obtained as J minus epsilon EB divided by 1 minus epsilon. If I put it here in this equation itself, what we get is Q by A net comes out to be epsilon B minus J divided by 1 minus epsilon by epsilon. Okay. So what does this equation tells me? This is a very important question. This is a very important question. Very often we miss the importance of this equation. What this equation is giving? This equation precisely gives me how the gray bodies are different compared to the black bodies. Okay, this equation gives me. So if I'm having the black body, in the black body, whatever the heat loss, how I am going to, heat loss will be there, and whatever the heat loss, the heat coming in will be there. That subtraction will give you the heat loss. But in this case, this equation gives me what? This equation gives me epsilon B is the term, and then there is a term J. Epsilon B is the emissive power of a black body. Epsilon B is there. So this is nothing but if my body is a perfectly black body instead of a gray body, how much will be the emission that I can calculate by epsilon B? Isn't it? And J is what? J is nothing but the amount of heat coming out from the gray body. It could be emission, it could be reflection, both, isn't it? How these are related to the net rate of heat loss from the surface, that you can directly calculate from this equation. But this equation gives another meaning in the sense that how I can relate epsilon B and J. There will be a resistance term coming in the denominator. What does this resistance term basically means? This resistance term is what? Remember, in this case, we are accounting. So when we are taking a real bodies or a gray bodies, J is important and not epsilon B. But here we are relating epsilon B and J. And what term is relating them is 1 minus epsilon by epsilon A, which we are calling it as a resistance term. Resistance term. So what this resistance will be? This resistance is nothing but a surface resistance. This is nothing but the surface resistance. Okay, surface resistance in the sense why? Why I am calling this as a surface resistance? Because this is only coming because my surface is not a black body, but instead it's a gray body. That's why this additional term as a resistance coming into the picture. And that's why we are calling this as a surface resistance term. Does it make sense to everyone? Hello? Hello? Am I audible?
Yes, sir.
Yes, sir, you are audible.
Okay, all right. So up to this we have seen in the last class. Now let's generalize this to a body in which we are having n enclosures. Remember earlier we have only looked at the n enclosure but with only black bodies. Now we are slowly moving from a ideal body to a more realistic body. We are saying that the gray body is a more realistic body because most of the real surfaces are close to the gray body. That's why we are, slightly deviating from the black body to the gray body. Okay. So in case of a gray body enclosure, there are, let's say, n surfaces are there, and these n surfaces are enclosed into a single body. How my heat loss will be related, that we are going to look at. Okay. In this case, we have looked at only one gray surface. Okay. So we are having a gray enclosure. Radiation from each of the n surfaces will be in general. Okay. So if we are having n surfaces, so what will happen? All these n surfaces will, emit the energy in terms of, it will, leave the energy in terms of the radiosity, and that will be incident, or that will act as a irradiation to the other surfaces. Do you all agree? Isn't it?
Yes, sir.
So all bodies will, give out the energy in terms of radiosity, but radiosity of one surface will act as a irradiation to the another surface, isn't it? So that's what is written here. Radiation from each of n surfaces will be in general be incident on all surfaces. If you consider, let's say, ith surface. So ith surface, the irradiation from the ith surface will be given by Gi. The irradiation on the ith surface will be because of what? It will be because of the remaining n surfaces, including itself. Isn't it? Do you all agree? Isn't it? So irradiation Gi of the surface will be the sum of the radiosity of n surfaces multiplied by respective areas and view factors. Do you all agree? Yes or no?
Can you please repeat?
Okay. So we are saying that we are having the n surfaces enclosed and a gray enclosure we have formed. Here all n surfaces are a gray surfaces. Now what will happen here? Each of the surface will, give out the energy in terms of radiosity, which could have the component as a emission component, and it will also have a component from the reflection. Okay. Now the irradiation received by any surface, any ith surface will be what? Irradiation received by any ith surface. Irradiation is what? Irradiation is the amount of radiation incident on the surface. Isn't it, per unit area? So irradiation on any ith surface will be given by Gi. But this irradiation will be what? This irradiation is primarily because of radiosity of all the other surfaces. Do you all agree? This irradiation on ith, remember this is an enclosure. Okay, maybe I'll just draw to make things clear to you. Just a minute. Okay, so let's say we are having This is the gray enclosure. Let's say this is 1, this is 2, this is 3, 4 and 5. Let us take surface 1. Now surface 1, whatever the radiation received here in terms of irradiation GI will be because of what? Will be because of the radiosity from this, radiosity from this, radiosity from this, radiosity from this. Also it could come from the surface 1 also if this surface is curved. Do you all agree?
Yes, sir.
But how much, see, radiosity, whatever the radiosity coming out from surface 2, 3, 4 and 5, not all will be incident on 1. Only the part of that will be incident on 1. And that part of that incident will be incident on 1 depends on what? It depends on the shape factors, isn't it? Whatever the shape factor I am going to have and the area, based on that, the fraction will be incident on 1, isn't it? So this Fi, this shape factor Fji, very important because that decides what fraction of J, what fraction of the radiation started from J will be reaching at I, isn't it? Do you all agree?
Sir, I have a question.
Please go ahead.
The one surface, for the one surface, we consider for one also itself.
Yes.
The radius due to itself.
Yes.
Okay, okay.
So if let's say we are having this one surface, I have shown a plane surface here, but instead of that, let's say if you are having a concave surface like this, what will happen? Radiosity from here can come here as a irradiation, yes or no?
Yes, sir. Yes, sir. Got it.
Okay. So that's what is written here. So AI, if you look at this expression, AIGI is nothing but what? AIGI is nothing but the amount of radiation incident on the surface I should be obtained as summation of all the radiosity from other surfaces multiplied by its shape factors and AJ. That summation will give this. Do you all agree with this equation? Do you all agree with me? So in this expression, J, capital J is what? Capital J is nothing but the radiosity. Radiosity is nothing but the radiation coming out from the jth surfaces, all the jth surfaces, and J is starting from 1 to n. But not all the radiation will be incident on I. So what will be the fraction of that? The fraction will be multiplied by Fji. Fji is nothing but what? The shape factor with respect to I. Yes or no? Fgi is nothing but the shape factor of J with respect to I. Yes, and that summation over all the surfaces will give me AIGI. Yes or no? Does it make sense?
Yes, sir.
Hello? Hello?
Yes, sir.
Okay, all right.
Yes, yes.
My slides are visible or I lost?
Visible.
Hello? Visible?
Visible, sir.
Just a minute. Let me make it full screen. Is it visible?
Yes, sir.
Yes, sir.
Okay. So now from this, argument, what we can write here is AIGI. AIGI, why we are multiplying AI here? Why we are multiplying AI in both? Remember GI and GI, these are per unit area. Remember? Yes or no? If I go back here, see what we have defined. Irradiation is per unit area. Radiosity is what? Per unit area. So the total amount of heat given in the form of radiation or received in the form of radiation, if I wanted to calculate, I have to multiply area. That's why the area is multiplied here. Do you all agree? Yes or no?
Yes, sir.
Okay, all right. Now AI in this case AIGI is given as summation of J equals to 1 to n AJ FJI JJ. This is what we have obtained from this argument which we have given here. Now, what is the first property of the shape factor. AI, AJ, FJI will be given by what? AI, Fij. That is the reciprocal relation. Do you all agree? Yes or no?
Yes.
So we can replace this AJ, FJI as AI, Fij. We can replace. Okay. Now, this is the net amount of irradiation received, irradiation or the radiation received by ith surface. What we are interested in? We are interested in calculating the net radiative heat loss from the ith surface. Now, net rate of heat loss from the ith surface is given by what? It is given by how much the heat is going out in terms of radiosity minus how much heat I am receiving in terms of irradiation. That difference is nothing but the net radiative heat loss. So for net radiative heat loss from ith surface is given by what? This AI, this area I am multiplying because this Ji and Gi both are per unit area. That's why AI is multiplied here. Is given as difference between radiosity and irradiation. Does it make sense to everyone? This first part is making sense to everyone? Hello? Hello?
Yes, sir. Yes, sir.
So now here we can expand this AIGI, AIGI and AIGI, AIGGI that we can replace by this equation. AIFij summation J1 to N, AIFijJJ. That is what we have replaced here. Now AIJJI is there. We already know that the summation of the shape factor, summation of all the shape factors Fij is just equals to 1. So if I multiply this summation directly here, Aij, does it going to make any difference? Because its summation is just 1. If I multiply this factor here additionally, it doesn't make any difference, isn't it? So that's what I have multiplied here, because even after multiplying this additional factor here, it doesn't make any difference because Fij is just 1. Summation of Fij over 1 to N is just 1. Does it make sense to everyone what I'm saying?
Yes, sir.
But now after multiplying this, I can now simplify, because now I can take this common Aij, AIFij, this I can take common, AIFij I can take common, and what will be the difference? The difference will be Ji minus Jj. So Qi net is given as AIFij Ji minus Jj. So what it means? It means that, okay, how much amount of heat loss I am having with respect to individual pairs. So when I am saying Ji minus Jj, this is nothing but the amount of heat loss between I and J specifically. So that gives me Qij net. Remember here Qi net. Qi net is what? Qi net is the net radiative heat loss from the ith surface to all the remaining surfaces. All the surfaces. But what Qij net is? Qij net is nothing but the net radiative heat loss from the surface I to surface J. To surface J. And how many surfaces J are there? 1 to N. So summation over all these J surfaces 1 to N, that gives me the total radiative heat loss from the ith surface. Does it make sense to everyone? Equation number 26.
Yes, sir.
Does it make sense to everyone? Yes or no? Hello?
Yes, sir.
Yes, sir.
Okay. So Qij net is nothing but the net radiative heat loss between the pair I and J. Okay. Now, but Qi net is the net radiative heat loss from I surface to all the surfaces, not just J, all the surfaces. Okay. So Qi net is given by this equation, but Qi net we have already calculated earlier, isn't it? What is Qi net is given by? Qi net is given by Ebi minus Ji divided by 1 minus epsilon by epsilon. Yes or no? Equation number 25. Correct? Does it make sense? So that,
Yes, sir.
So that's what we have written. Qi net is EBI minus GI divided by 1 minus epsilon I divided by epsilon I AI. Okay. Again, this second equation, this second part we can rearrange. We can take this AI Fij in the denominator, so that becomes 1 upon AI Fij. So we are representing this denominator term in terms of a resistance. Okay. Now, two important things are coming into the picture. When I am changing from EBI, remember here, when I am changing from EBI to JI, I have a resistance term given by 1 minus epsilon I divided by EI. Isn't it? That is the resistance term coming into the picture. But when I am changing from JI to JJ, in that case, the another resistance term comes into the picture in the denominator, that is 1 upon AI Fij. Now, this first resistance term here, this first resistance term, which is 1 minus EI divided by EI, this first resistance term, we have called this first resistance term as surface resistance, isn't it? That's what we have called. Yes or no? This term we have called as a surface resistance. Do you all agree? When I am moving my cursor, is it visible to everyone?
Yes, sir.
Yes.
So this particular term we have called as a surface resistance. Do you agree? This is what I said in the last slide. But what this resistance is called as? This resistance is called as space resistance. This is called as a space resistance. Why we are calling this as a space resistance? Because here this Fij factor is coming into the picture. And what is Fij? Fij is nothing but the shape factor or view factor. So how much part of the other surface I am able to view, that defines how much will be the radiation coming into the particular surface. So this particular resistance is called as a shape, a space resistance, and this is called as a surface resistance. Okay. A minute difference is there, but unless you visualize it, you will not appreciate these concepts. Okay, there's a lot of details are there, and very interesting details are there. Okay, very often when we look at the radiation, we only look at the black body. We don't even consider the gray bodies or real bodies, isn't it? This gives a real picture. This gives a real flavor that what type of resistances come into the picture when we talk about the real surfaces and not the black bodies. Does it make sense to everyone? Hello? Does it make sense to everyone? So when we are talking about just comparing JI and JJ, then this resistance comes. When we are talking about EBI and JI, so this is the black body to gray surface, then this resistance is coming. That's why it is called as a surface resistance, because you are changing surface from black to gray. In this case, both are gray surfaces. JI is also gray, JJ is also gray. But when we are looking at the radiative heat transfer between them, the resistance come into the picture is nothing but 1 upon AI Fij. This is with respect to what? This is with respect to the shape factor and view factor, and therefore we call these as a space resistance. Space resistance. Okay. Things will be clear when we will look at a simple manual calculation with respect to this. Now let's look at only two gray surfaces. We will try to expand these complicated equations here, which you might have lost so far. But when we will look at expanded form of these for surface 1 and surface 2, we will appreciate these concepts a little bit more. Does it make sense? Hello? Does it make sense to everyone what I'm saying?
Yes, sir.
So let us expand these complicated equations for two surfaces. Let's assume that the enclosure is having only two surfaces, and we are manually expanding this so that we can appreciate what it means. Okay, so let's look at the surface 1. So I equals to 1. I can write this equation for I equals to 1. I can expand this equation for I equals to 1, isn't it? For I equals to 1, I can write this as EB1 minus J1 divided by 1 minus epsilon 1 divided by epsilon 1 A1. And that should be equals to what? What will be the right hand side? What will be the right hand side here? Sorry. 1 to 2. 1 to 2 AI A1 F11 F F11 J1 minus J1. So that will be the first term will be 0. So we will have only a second term available, and that second term will be what? A2 F2 sorry, AI is there. So A1 F12 F1 J1 minus J2, isn't it? That's what we are going to get. So that's what we have obtained. A1 F12 J1 minus J2. Do you agree? The first term with respect to J equals to 1, that will be 0 because J1 minus J1 will be 0. Do you all agree? Does it make sense?
Yes, sir. Yes, sir.
Similarly, we can write down the expression for I equals to 2. So this is the expression for I equals to 2. This is the equation for I equals to 1. This is the expression for I equals to 2. Now let us subtract both these equations. Let us subtract both these equations. So if we subtract both these equations, what we are going to get? So see, this resistance term I can multiply on the right hand side. This resistance term I can multiply to the right hand side. And if I subtract both these equation, this I equals to 1 and I equals to 2, what I'm going to get? EB1 minus EB2. This will be a first term. There will be another term will be there minus J1 minus J2, and that minus J1 minus J2 term I can take it on the right hand side, and that J1 minus J2 term will be common throughout this, isn't it? So that I can take it common. Does it make sense to everyone? What we have done? Also,
Yes,
also F12 we are representing everything in terms of F12. So F21 will be given by what? F21 will be given by A1 F12 divided by A2. Yes or no? Everything, this entire equation we have written in terms of F12. So F21 is there. This F21 term is there. This F21 term I can get rid of this F21 term by this equation. So F21 will be what? F12 into A1 divided by A2. Do you all agree with me? Yes or no? Hello?
yes, sir.
So with this simplification, we get this equation number 29. So now this equation number 29, okay, so this entire bracketed term is there. This entire bracketed term is there. Now net radiative heat loss. Net radiative heat loss is given by what? EB1 minus J1 divided by 1 minus epsilon 1 by A1. This is the net radiative heat loss from the surface 1, isn't it? Correct. But right hand side is J1 minus J2. So this J1 minus J2 term which is here, that I can replace by EB1 minus EB2 divided by this entire bracket. Do you all agree? And if I put that in this equation, I get this equation number 30. Does it make sense to everyone? How we got equation number 30? Remember, equation number 29 gives me the expression for J1 minus J2. J1 minus J2 will be what? EB1 minus EB2 divided by this entire bracket, which is there on the right hand side. Now this J1 minus J2 term, I can put it here in the first equation for I equals to 1. J1 minus J2 term I can replace here. So if I replace that, what I get is Qi net is given as EB1 minus J1 divided by 1 minus epsilon 1 divided by epsilon 1 by A1. And right hand side will be EB1 minus EB2 divided by 1 minus epsilon 1 divided by epsilon 1 by A1 plus 1 by A1 F12 plus 1 minus epsilon 2 by epsilon 2 by A2. Okay, this is what we are going to get. Now this equation number 30 is really interesting. Why it is really interesting? Can anybody say why it is really interesting?
We get it all in terms of resistances added.
This equation number 30 is really interesting because let's say if this body 1 and body 2 would have been black bodies, let's say purely a black body, what we would have obtained? Equation 30 would have been what? It would have been just sigma into A into T1 raised to power 4 minus T2 raised to power 4. Yes or no?
Yes, sir.
But we are getting the additional resistance terms in the denominator because we are not looking at the black bodies. Instead of that, we are looking at more real gray bodies, isn't it? And these three resistance terms we are getting. So what is the first resistance term? 1 minus epsilon 1 divided by epsilon 1 A1. This is the resistance term which converts the emissive power to J1. Emissive power EB1 to J1. Remember EB1 to J1, this is the denominator term I am getting. Can you see? Yes or no? And between J1 and J2, what is the resistance term? A1 F12. That's what we have seen earlier. J1 to J2, A1 divided by F12. Do you agree? And from J2 to EB2, the another resistance term is what? 1 minus epsilon 2 divided by epsilon 2 A2. This is the another resistance term coming in. Now this first term and this last term here in the denominator, these are nothing but what? These are nothing but surface resistance of surface 1 and surface 2. Do you all agree? Correct?
Yes, sir.
Whereas this middle term here is the space resistance student. So this is very interesting. We have started the concept of black body, but now we are moving to a more realistic bodies. So this entire denominator term, you can write this entire denominator term as effective emissivity. Effective emissivity. Remember, this entire denominator term, if I represent here A into epsilon overall, that will represent the overall emissivity. Does it make sense? Yes or no? Hello? Does it make sense or not? I think
Yes, sir.
students have lost here. These are really interesting. You have to, look at each of these terms in the perspective. Don't look at these as the equations. If you look at this in a conceptual point of view, you will appreciate this. How we have, digressed from that, ideal black surfaces to a gray surfaces. How additional factors and resistance terms come into the picture. There are two types of resistances comes into the picture. First is the surface resistance, which basically looks at how the J and EB term are related. So EB term you get only for a black body, but J term you get it for a real bodies or a gray bodies, isn't it? So how this difference is related, and this difference is related by a resistance term which is nothing but the surface resistance. But when you are looking at one J to another J, the resistance term come into the picture is nothing but the space resistance, which is corresponding to what part of that surface is visible to the another surface. And that's why only the view factor coming into the picture here. This is a space resistance. Okay. And all these two resistances comes into the picture when we are looking at the transfer of heat from one gray body to another gray body. These resistances are not there when we are looking at this heat transfer from a black body to another black body. Make sense to everyone? Hello?
Yes, sir.
Okay, so now this is again just to appreciate more. These are represented in a circuit diagram like this. So here you can see EB1 to J1, this resistance is present. From J1 to J2, this another resistance, space resistance is present. And from J2 to EB2, this another resistance is present, which is nothing but the surface resistance for surface 2. Now this equation number 30 we can further simplify. Let's assume that infinite parallel plates are there. So infinite parallel plates means their view factors F12 will be just 1. Also their ratio of the areas will be just 1. And if let's say if we assume these two conditions, what we are going to get? Qi net by A1 will be given by what? This numerator remain as it is, sigma into T1 raised to power 4 minus T2 raised to power 4 divided by denominator is 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So this 1 minus epsilon 1, 1 minus epsilon 2 and plus 1 is there, and this additional 1 term here and plus 1 term here that get cancelled out. Okay. Is it clear to everyone? Hello?
Yes, sir.
So you will see that very often this equation people use. In fact, in your JEE days, you might have used this expression directly. I am not sure whether you have derived it. Is it? Have you used this equation ever in your JEE days?
No, sir. I think no gray bodies were.
Okay, you have not used. Okay, all right, all right. Okay. So now let's extend this concept to something called as a radiation shield. Radiation shield is nothing but the application of these concepts to reduce the radiative heat loss. Let's say we are looking at the radiative heat loss between wall 1 and wall 2. So if I add another fictitious wall here in between, maybe some transparent wall here in between, you know, by addition of another radiation shield in between, how we can reduce the radiation loss between body 1 and body 2. That's what we are looking at. Let's say wall 1 and wall 2 are there, and with the assumption that these are the infinite parallel plates, so their ratio of areas is 1 and their shape factor, view factor, which is just equals to 1. So Q12 by A will be given by the same expression, sigma T1 raised to power 4 minus T2 raised to power 4 divided by 1 plus 1 by epsilon 1 plus 1 by epsilon 2 minus 1. So this is the same expression I am writing. OK. Similarly, if I add a radiation shield in between, so then in that case, there are two types of radiation will occurring, isn't it? From wall 1 to wall 3 and from wall 3 to wall 2. So from wall 1 to 3, the radiative heat loss will be given by what? Q13 by A. And again, we can write down this expression as sigma T1 raised to power 4 minus T3 raised to power 4 divided by 1 by epsilon 1 plus 1 by epsilon 3 minus 1. Similarly, Q32 will be written by what? Sigma T3 raised to power 4 minus T2 raised to power 4 divided by 1 by epsilon 3 plus 1 by epsilon 2 minus 1. OK. But as I said that the radiation shield is a barrier wall of low emissivity placed between two walls in order to reduce the exchange of radiation between them. Radiation shield is added in between so that we can reduce the radiative heat loss between 1 and 2. Now with this addition of radiation shield here, isn't it? This radiation shield is basically does what? It maintains the equilibrium. Whatever the radiation it receives, the same radiations are given to the wall 2, isn't it? Now this is something what we have seen earlier also. If you look at, remember here also we have seen that this refractory wall, whatever the radiation it was receiving, the same it was emitting, isn't it? Do you all agree? Yes or no? So similar to that, not exactly the same, but similar to that, here also we are assuming that whatever the radiation is received by shield, the same amount of radiations are transferred to the radiosity is transferred to the wall 2. So net radiative heat loss Q13 by A and Q32 by A both are same. So if we equate these two equations, we can find out what will be the equilibrium temperature T3 here. So equilibrium temperature, again, if you assume a special case that the emissivity of all these three surfaces are same, epsilon 1 is equals to epsilon 2 and equals to epsilon 3, and all are equals to just epsilon. In that case, we can get the equilibrium temperature T3 as equilibrium temperature T3 comes out to be T3 raised to power 4 is given as T1 raised to power 4 plus T2 raised to power 4 divided by 2, just by rearranging this. Remember, if this epsilon 1, epsilon 3 and epsilon 2 both are all are same, in that case, we can equate this temperature difference with another temperature difference, and finally we can obtain this. Do you all agree? Yes or no?
Yes, sir.
And if you put this T3 raised to power in this original equation Q13 here, Q13 if you add in this Q13, if you add this T3, so what ultimately you get? Ultimately you get Q13 net is half of the Q12 net. Q12 net, whatever Q12 we have obtained earlier, only half of that you are going to get. So what we are concluding here, just by adding a radiation shield with the same emissivity as that of surface 1 and surface 2, my radiative heat loss is reduced by 50%. Isn't it? I have not even used the low emissivity shield in between. I have used the same emissivity just for a simplicity. Just to appreciate the concept. And you can see that the radiation heat loss is there. Remember, in this case, what we are saying, the amount of radiation coming from T1 to T3, the same is being transferred from T3 to T2. So that means Q13 is same as Q32, isn't it? And when this shield is there, the net radiative heat loss is what? Is same as Q13 and Q12, isn't it? There's no radiative heat loss from surface 1 to 2 directly. So net radiative heat loss when I'm having the shield in between is just Q13, isn't it? But when I'm not having the shield in between, that the net radiative heat loss is Q12. And if I compare Q12 with Q13, Q13 is 50% lower than the Q12. Does it make sense to everyone? Hello?
Yes, sir.
I may ask you a very hypothetical question that let's say if I wanted to reduce the heat loss by 75%, how many radiation shield are required? You can calculate that, isn't it? Yes or no?
Won't it be 2 half each time?
Please repeat what you are saying.
Sir, won't the number be 2?
Number will be 2. Why? In which case?
50% reduction takes place with each radiation shield.
So
if
in
we place
75% reduction will be 2. That's what you are saying?
Yes, sir.
Yes.
Sir.
But see, these are with respect to this assumption that the emissivities are same.
Yes,
if I'm
sir,
having
yes, sir,
this emissivity is different, it might not be the true, isn't it? You might require more number of shields or less number of shields. Correct? Does it make sense?
Yes, sir.
Okay, so there is now a last concept of radiation is there. So far we started with conduction, then we started with convection, then we have looked at the radiation. Now I am bringing a system in which all three are present. There is a conduction, there is a convection, and there is a radiation. So let's look at, there is a conducting wall with a high temperature is there. So inner temperature is Ti, outer temperature here is T0. Outer temperature here is T0 because the radiation heat loss from this outer surface takes place by both radiation as well as convection. But here between this wall, the radiation the heat transfer is taking place by conduction here. So all three heat transfer mode are present here. So I can write down the balance equation. So net heat conducted through this wall will be given by K by L Ti minus T0. Do you all agree? Yes or no?
Yes, sir.
And that should be equals to the heat taken out by radiation as well as convection. So right hand side I will have two terms. Convection term will be given by what? Newton's law of cooling. So that is nothing but H delta T. Now delta T will be what here outside? T0, which is nothing but the surface temperature. And what is the ambient temperature here is Ta. So H into T0 minus Ta is nothing but the heat loss by convection. Do you agree? Correct? Yes or no?
Yes, sir. Yes, sir.
Similarly, the heat loss by radiation will be given by what? Epsilon into sigma T0 raised to the power 4 minus Ta raised to the power 4. Do you agree this last term? Make sense to everyone? Hello?
Yes, sir.
Now, very often what we do is, remember in this case, there is no temperature difference. This is not an ordinary temperature difference. Here temperature raised to the power 4 we are taking and then subtracting. And also these temperatures has to be taken in Kelvin, not in degree centigrade. Here, even if you take it in degree centigrade, doesn't matter because that plus 273 get cancelled out, but that is not the case here. So be cautious when we are calculating the net radiative heat loss in terms of radiation. Okay, this is the common mistake people do. Okay, so here this entire term I can represent, this radiation term I can represent similar to the convection term. Let's say if I put this entire term as, this entire term I can represent as HR T0 minus Ta, where HR is nothing but what? HR is nothing but radiation heat transfer coefficient for the radiation. Transfer coefficient. Remember, heat transfer coefficient, this concept is only for convection. But here we are talking about heat transfer coefficient for radiation. So what we are actually saying here is we are representing this radiation term similar to convection. So what this HR will be given by what? This HR will be given by what? Sigma into T naught raised to power 4 minus TA raised to power 4 divided by T naught minus TA. Do you agree? Yes or no? Does it make sense? Does it make sense or not?
Epsilon.
Hi, epsilon will be there. Correct. Sorry.
Yeah.
Here also we will have a epsilon term. Does it make sense to everyone?
This is for replacing only the radiation, not the
Radiation part.
convection.
So okay, so once we have replaced this by HR, if we replace by HR, then this entire bracket, let me show it by a different color. Then this entire bracket we can represent separately as H naught T naught minus TA, where H naught is nothing but what? HC. Let's say this is, I represent this as HC convection, HC plus HR. Do you agree? Does it make sense?
Yes, sir.
So very often, this type of question are also there. People say that the radiation heat transfer coefficient is there. Radiation heat transfer coefficient. Of course, the heat transfer coefficient concept is not for the radiation. It is developed for convection, but we can extend that for radiation. This is what the extension is, which I'm, giving you. Clear to everyone? Hello? Does it make sense to everyone?
Yes, sir.
Yes, yes, sir.
Okay. So let's move to the next slide. Let me discard this. Is it visible? My slides are visible to everyone? Hello? Hello?
Yes, sir, they are visible. Yes.
So let's look at two problems to appreciate the concepts. Okay. So problem one, a carbon steel sphere of 0.3 meter in diameter at 800 Kelvin cools down by radiative heat loss to an ambient at 303 Kelvin. If other modes of the heat loss are neglected, this is very important. Other modes of heat loss are neglected. These other modes of heat loss are neglected. And if the ball and the ambient are assumed to be black. When I'm saying assumed to be black means what? Emissivity is 1, isn't it? So the additional factor which comes into the denominator otherwise is not there. Correct? Yes or no? So calculate the time required for the ball to cool down to 343 Kelvin. The density and specific heat of the carbon steel are 7801 kg per meter cube and specific heat is 473 kilojoule per kg per degree Celsius respectively. This is very simple problem. Similar problem we have seen for natural convection. Similar problem we have seen for forced convection, and now the same problem we are seeing for radiation. The rationale behind using the same problem is to appreciate the same concept for three modes of heat transfer. Does it make sense? Similar problem we have already seen earlier. Does it make sense to everyone what I'm saying? Hello? Hello?
Yes, sir.
Your yes is not having that confidence. Sorry. Is it clear? Hello?
Yes, sir.
Okay, please say confidently. If it is something is not clear, I will not hesitate to, do it again and again. Please say so. If something is not clear, please say so. Okay, so let's look at the balance equation here. Okay, so in this case, the net radiative heat loss will be given by Q12 as A1 F12 sigma T1 raised to power 4 divided by T1 raised to power 4 minus T2 raised to power 4. And this entire term we are not having divided by any other term. Remember, in a real surfaces, we would have had this additional term something like this, isn't it? If I would have used the real surfaces for the real or a gray surfaces, I would have had the term something like this. Q12 will be given by sigma T1 raised to power 4, T2 raised to power 4 divided by, I would have had this term 1 minus epsilon 1 divided by A1 epsilon 1 plus 1 by A1 F12 plus 1 minus epsilon 2 divided by A2 epsilon 2. This was the equation, isn't it? When I'm having the gray bodies. But instead of, I'm not using this equation at all. Why? Because my surfaces are black. Makes sense to everyone what I'm saying? Does it make sense to everyone what I'm saying?
Yes,
Sir,
sir.
for black body, we won't consider F12 either.
F12 will be there. F12 is a shear factor. Isn't it? That
Okay,
depends
F12
on.
would be there. Okay.
F12 is a shear factor. No, F12 depends. So see, if I am having, let's say, two bodies, if I am having two bodies, let's say both are black. Let me do it again. I am having two bodies. So how much radiation going here and how much radiation going here, net difference between them depends on the shear factor F12, isn't it? Yes,
Sir,
or
I
no?
was just saying because the ambience was there, so they
So
ultimately
ambience, okay.
the
So F12 will be in this case just 1. You are absolutely correct. Yes, F12 will, because
yes,
both ambience is there. Yes, you are absolutely correct. If you are saying in that way, it's perfectly all right. Okay. So that's what we have also written here. F12 is just 1. Okay, all right. Because all the radiation emitted by the sphere will be intercepted by the surrounding. That means its shape factor will be just 1. Right. Now what is been given here? So this is the rate of radiation loss from the radiation, isn't it? And that loss by radiation will be reflected in terms of what? In terms of change in the internal energy of the sphere. Yes or no? So at what rate the temperature of the sphere is decreasing, that is what is deciding how much the radiation is going out. Correct. So MCP d by dt of T will be same as the radiative heat loss, isn't it? Correct. So that's what we have written here. T by dt MCPT is nothing but the radiative heat loss Q12. So if we rearrange everything, so this M I can directly calculate it. This density is given, this diameter of the sphere is given. So from this diameter of the sphere, we can find out the volume of the sphere multiplied by density gives me the mass of the sphere. So mass here multiplied into Cp is already given. So mass into Cp, I can take it out, and dt1 by dt I can have here, isn't it? And right hand side, I will have A1 F12 sigma T1 raised to power 4 minus T2 raised to power 4, and F12 is just 1, but area A1 I can calculate, that is 2827, isn't it? So everything is known in this equation, except that we wanted to find out the time for cooling down the sphere from 800 to 343, isn't it? Correct. So this integration we have to solve, isn't it? This integration we have to solve. So we wanted to find out the time to cool down the sphere from 800 to 343. If we solve this integration, what we get is the time comes out to be 36930 seconds. Is it clear to everyone? Does it make sense to everyone? Hello? Hello? A similar problem we have solved earlier using the forced convection and this natural convection. Make sense to everyone now?
Yes, sir.
Okay, now here until now we are only looking at a black body. But what will happen? Let's say this black body is not a black, but instead it is a gray body. And instead of a spherical surface which is present in the surrounding, let's say a curved surfaces are there which has the shape factor with respect to itself, what will happen? Let's look at another problem on such concept. So we are having a gray body with the emissivity of 0.6. So we are not having a black body, we are having a gray body which has the emissivity 0.6. Shape factor 0.4 with respect to itself means what? F11 is just 0.4. Do you agree? So what will be F12? Anybody? If I have a F11 equals to 0.4, what will be F12?
0.6.
Point. Hello. 0.6. Why 0.6?
1 minus.
Because that property number 4 is there, shape factor, isn't it? F11 plus F12, and that summation goes all the way to F1n. That summation should be equals to 1. Since we are talking about only two bodies here, F11 plus F12 should be equals to 1. And since F11 is given at 0.4, F12 will be 0.6. Does it make sense to everyone? Again, everything is given here. So mass is given, specific heat, specific gravity is given, specific heat is given. The body is initially at 200 degrees Celsius, exposed to the environment at 30 degrees Celsius. We wanted to find out the time required for temperature drop to 40 degrees Celsius, the convective heat transfer coefficient. Again, in addition to, so here not only we are talking about the radiation, but also the convection is also taking place. So both convection and radiation are taking place. Okay, and the heat transfer area is also given here. So in this case, we wanted to find out the time for decreasing the temperature from 473, that is 200 degrees Celsius, to 313, which is nothing but 40 degrees Celsius. That time we wanted to find out. Okay, F11 is 0.4, so F12 comes out to be 1 minus 0.4 is 0.6. Area is given. Area is 300 centimeter square is given, so that is 0.03 meter square. CP is given 500 joule per kg. Okay, mass is given as 2 kg, and epsilon 1 emissivity is given 0.6. This is occurring in the surrounding. So what will be the epsilon 2? What will be the value of epsilon 2? Anyone? Remember, epsilon 1 is given 0.6, but we require epsilon 2 also. What will be epsilon 2?
1.
Epsilon 2 will be 1 because environment is there, that is vast, infinite is there, isn't it? So whatever goes in the environment, it gets completely absorbed, isn't it? So its emissivity is 1. Whenever such case is there and the emissivity is not mentioned for the environment, big environment outside. Of course, if you are having the enclosure, then the matter is different. But when we are having a open environment, the way we are talking about here, in that case, its emissivity is 1. Okay. So this is what the equation we have to use. Now this equation is different, isn't it? Remember earlier we have used a different equation, but we are talking about the gray body. So our expression now changed. Does it make sense to everyone? Hello?
Yes, sir.
So now this is the net radiative heat loss. This is the net radiative heat loss. So in this case, I can put all the values here. Epsilon 2 is just 1. So epsilon 2 is 1. So 1 minus 1 is 0. So this last term get cancelled out. So if I put all the values, only these two terms will be there in the denominator. So if you put all these terms, only T1 is unknown here. T2 is the ambient temperature, so that we know. But T1 is changing. T1 is changing from what? 200 to 30 degrees Celsius. So in terms of 200 to 40 degrees Celsius. So this is changing from 473 to 313 Kelvin, isn't it? So at every time this T is going to change. That's why we have kept this as a unknown here. Now this is a net radiative heat loss. Similarly, we will have a convective heat loss. So convective heat loss will be given by what? HA1 T1 minus T2. Do we agree? Here also this T1 will be unknown. H we have already given 25 watt per meter square. So 25 into area. Area is, we have calculated this 0.03 into T1 minus 313. Now both these net radiative heat loss plus net convective heat loss, this will be the heat loss from the surface. and this heat loss from the surface will lead to the decrease in the temperature. So mCp dt by dt will be given by this total net radiative heat loss in terms of energy balance. So that's what we have to write. Minus d by dt mCpt. This is minus mCp dt by dt will be given by this summation of both these factors. Correct? Does it make sense to everyone? Now I can integrate this equation. I can integrate this equation between these limits 473 to 313 and I can find out the time required. So that's what we have done. 473 to 313. We have integrated this equation. So time comes out to be 3180 seconds. Is it clear to everyone what we have done? Hello? Hello? Does it make sense?
Yes, sir.
Okay, so this is all about the radiation. Let us move to the next chapter, which is nothing but the heat transfer equipments. So let me share the file. We will do some preliminary things on that, and then we will discuss our, when we will be having a quiz and the classes. Okay, so let me share the another file without wasting any time. So is it visible? This new slides are visible to everyone? Hello?
Yes, sir, they are visible.
Okay. So far we have looked at we started with conduction, convection, radiation, condensation. We have looked at, isn't it? Boiling and condensation we have used. We have looked at. And now let's look at heat exchangers. Okay. So heat exchangers, if you look at, is very important in the process application, because if you work in the process, I don't know whether you will join the chemical industry or not, but if you join a chemical industry, then in all chemical industry, you will see the heat exchangers, different type of heat exchangers. So designing of that, what are the different designs are there, which design is suitable for what, all these concepts we are going to look at in this particular chapter. Okay, so heat exchanger are one of the commonly used equipment in the process industry, as I said. Again, if you look at the heat exchangers, so whenever we are looking at the heat exchanger, these are, facilitate the transfer of heat not only from solid to fluid, but very often fluid to fluid or gas to liquid, all type of, heat transfer we see in the process application. Okay, again, sometimes the two fluids are, so see, when two fluids are in a direct contact with each other, that is called as a mixing. That is not called as a heat exchanger. So whenever we are saying the heat exchanger, the two fluids which are in a thermal contact, which are in the thermal contact with each other, but they are not direct contact with each other. So both the fluids are separated by a barrier in between. Very often that barrier is a metal wall. Very often the barrier is a metal wall. So for instance, if you look at a double pipe heat exchanger, so double pipe heat exchanger generally has what? It has two concentric pipes, isn't it? So inner pipe will have one fluid flowing, and in the annular region another fluid is flowing, and both these fluids are exchanging heat with each other. In between there is a metal wall, isn't it? That's what happens in the double pipe heat exchanger. In a plate type heat exchanger, there are different chambers are there between the plates, and in the chambers, in one chamber the hot fluid is there, in the another chamber there is a cold fluid is there, which are separated by a plate, and the heat transfer takes place across this plate. In a spiral heat exchanger, the spiral cavities are there. So in one spiral cavity the hot fluid is flowing, in another adjacent spiral cavity the cold fluid is flowing, and there is a heat transfer between them. Okay. This is a air cooler heat exchanger. So here the heat is taken out from the fluid by blowing the air over the pipe, by blowing or sucking the air over the pipe. Okay. Then there is a shell and tube heat exchanger. So in a shell and tube heat exchanger, there is a big size shell is there. That's nothing but a big size tube is there, and between this big size tube there are several small tubes are there inside. So one fluid is flowing through the shell and another fluid is flowing through this n number of tubes inside, and the heat exchange takes place between them. Okay, so shell and tube heat exchanger is a generalized version of this double pipe heat exchanger in a way. Yes, somebody is saying something.
Sir, what is the use or the purpose of the heat exchanger to reduce the heat wastage?
So no, not at all, not at all. The purpose of the heat exchanger is very often in the process industries. What happens is you need to transfer heat from one fluid to another. For instance, let's say, okay, so if you are working in a nuclear power plant, so heat is generated and that heat is taken away by what? That heat is often taken away by a heavy water. If you are looking at the normal nuclear reactor, if you are looking at a fast breeder reactor, there the heat is taken by a sodium liquid metal. So this heat taken by the sodium has to be transferred to a normal fluid so that you can run that normal fluid in a turbine. Got the point?
So I mean that sodium or D2O cannot be replaced by directly the solid which has directly the liquid that has to be heated.
No, not possible, not possible. Very often, because sodium, if it comes into contact with air, it generates the flame, isn't it? So no way it comes in the contact with the another. And in fact, why sodium? Because sodium has a very high, heat capacity. In fact, liquid metals are used in the nuclear reactor because they have very high heat capacity. That is the reason why heavy water is used in the nuclear reactor instead of a normal water. If this is the question people ask you, why nuclear reactor use a heavy water and not a normal water? So heavy water is what? Instead of hydrogen, you will have a tritium or a deuterium, isn't it? Because their heat capacity is higher than the normal water. It can carry more heat per kg compared to the normal water. So amount of heat generated is so high, you wanted to use the solvent which is more capable of transferring that heat effectively. Got the point?
Okay, sir.
This is one application. Another application I tell you. Okay, very often you perform the reaction in a reactor, but this reactor has to be heated. So how you heat the reactor? A steam or a hot fluid is passed through the jacket which is outside the reactor, isn't it? So heat transfer is is regularly used in the process application. Very often what happens is a hot flue gas coming from the reactor or maybe from the power plant. If you leave that hot flue gases directly in the environment, not only it will harm the environment, but also you are going to lose a heat to the environment directly instead of recovering that. More the heat you recover, better is your economics. Do you agree?
Yes, sir.
Isn't it? So very often we wanted to recover that heat, and that heat is recovered by what? By having the heat exchangers. Got the point? Does it make sense?
Yes.
So another example, another interesting example. So you might have looked at distillation column in your mass transfer, correct? So in the distillation column, you always have reboiler and condensers. So what these reboiler and condensers do? There's a heat generated. There's a heat generated by a steam, and that steam is hitting the another fluid, isn't it? Correct? That's what happens in the reboiler. In the condenser, the heat has to be recovered. If you are cooling a particular fluid, some other fluid is getting heated, correct? And that heat has to be recovered later. Otherwise, you will be losing the heat. And more the amount of heat you are losing in the process plant, more the money you are losing. Because how this heat is generated? This heat is generated by using either a steam or by burning of a gas, isn't it? So you are losing the heat, means you are losing the money. So very often the heat is recovered from one place and supplied to the other place where it is required. Got the point? Does it make sense?
Yes, sir.
So you recover the heat from one place and you give it to the another place where it is required. Otherwise, if you don't use the heat exchanger, what happens is you end up with heating one place by consuming energy, and you end up with cooling another place again by consuming energy. Got the point? Hello?
Yes, sir.
Okay. So double pipe heat exchanger. We will look at all these heat exchangers in little bit more detail to appreciate the concept further. So double pipe heat exchanger, as I said, double pipe heat exchanger has two concentric pipes. Here you can see you are having a outer pipe, and inside that there is a inner pipe. So one fluid is flowing through the inner pipe coming out from this, it is coming in here, it is coming out. Another fluid is coming here in the annular region and going out from the annular region. So the contacting here could be counter current or co-current. Okay, so in a cross section, if you look at the cross section, looks like this. So one fluid is flowing through this inner pipe, another fluid is flowing through this annular region outside. Okay, again, sometimes to increase the heat dissipation, what happens is this inside pipe, the outside surface of this inside pipe is corrugated or a fins are there. So fins, having more fins here means more heat transfer area, and that will enable the higher heat transfer. But at the same time, it also increase the chances of fouling. That means there is an unwanted deposit takes place on the surface. Okay, so more the corrugated surface is there, higher will be fouling, and you require a frequent cleaning of the inner tube will require. Is it clear to everyone what I'm saying?
No, sir. Sir, can you repeat?
So if we add, okay, if I add a fins here, let's say if I add a fins here, what will happen?
There may be accumulation of some, like,
There will be accumulation, but at the same time there will be more heat transfer also, isn't it? By adding a fins,
yes.
you are increasing the heat transfer area. Does it make sense?
Yes, sir.
But at the same time, more fins means you will have a, more accumulation of the dirt and other things will take place. Correct? So you will require a frequent cleaning of the tube. Yes, yes or no? Make sense?
Yes, sir. Yes,
Okay.
sir.
So now this generalized version of this double pipe heat exchanger is nothing but shell and tube heat exchanger. So shell and tube heat exchanger has multiple tubes inside one big shell. One big shell. Okay. That we will look at here. So this is a shell and tube heat exchanger. Here you can see that there are, I have just for a simplicity, I have shown only 4 tubes are there. 1, 2, 3, 4. These 4 tubes I have shown here, and these 4 tubes are present in a bigger size tube which is called as a shell. This is a bigger size tube. One fluid is coming in here. This is a shell side fluid coming in that follows a tortuous path like this because there are baffles are there in between, isn't it? And this fluid is coming out here. Another fluid is coming here in this cover type, head. So one fluid is coming here and that follows through these 2 tubes and coming out from this another 2 tubes. So this type of arrangement is called as one shell side pass and 2 tube side pass. So here you can see that the fluid in the tube side is going twice, isn't it? There is 2, it changes the direction like this, isn't it? So there are 2 tube side passes and 1 shell side passes. So one side passes is like this, tube side passes is going this and coming back like this, isn't it? So this
these blue pipes are the boundary of the, like, the wall
these
of the
blue
pipe.
pipes or these blue pipes you are saying?
No, sir.
This
the horizontal ones. The horizontal ones.
These horizontal ones are these blue pipes are not the boundary. One fluid is flowing through this. One fluid is flowing through this. This fluid coming in here. Just a minute, I will explain. So one fluid is flowing through this. Okay. And coming out from this. And another fluid which is this is moving like this outside this tube, follow this tortuous path and then coming out here. Correct? Is it clear?
Yes.
This is called as a shell and tube heat exchanger. So now, can you see the point why I am saying that this is a generalized version of double pipe heat exchanger? Because instead of only one inner pipe, I am having multiple inner pipes here. Can you see? If I look at the cross section, how the cross section will look like. So cross section will look like that. I am having a bigger size pipe, and there inside this bigger size pipe, I am having several. Inside this bigger size pipe, I am having the several small size pipes. So one fluid is flowing through these blue tubes and another fluid is flowing through this entire annular region around. Can you see the point? Is it clear?
Yes.
Does it make sense? Hello? Does it make sense to everyone? Okay. Okay, so let's look at the discussion here. So this is one of the most popular and important heat exchanger in the process industry because this is commonly used. This is very commonly used. You visit any process industry, you will find shell and tube heat exchanger. Okay, this is one of the most commonly used heat exchanger. It involves multiple tubes inside the container called as shell, as I said. The fluid flowing through tubes is referred as a tube side fluid. So whatever the fluid is flowing through these tubes inside, these are called, the fluid is called as a tube side fluid, whereas the fluid which is flowing through the shell is called as a shell side fluid. Usually multiple tube side passes are there. So in this case we have shown one, this is the one pass and this is the second pass. So this particular heat exchanger will be called by what? This will be called as 1-2 shell and tube heat exchanger. This is called as 1-2 shell and tube heat exchanger. So what is 1 represent? Shell side pass. Shell side pass. And what this 2 represent? Tube side pass. So how many shell side pass are there? You can see shell side pass, only one shell side pass is there, isn't it? It is going in only one direction like this, isn't it? However, tube side is going like this. This is one pass and then coming back like this, isn't it? So there are 2 tube side passes and 1 shell side pass. Is it clear to everyone? Hello? Does it make sense? Hello?
Sir, why we can take tube fluid out from there only?
Why we are taking 2 fluid out here? Here you are saying?
Yes, sir. We can take from the other side as well.
Here.
Is it to increase the heat exchanges?
So see, if I take the outlet, this outlet here, how many passes I will have in a tube side?
Only one.
So this particular heat exchanger is 1-2 shell and tube heat exchanger. That's why this outlet is here on this side. Okay, and this is a barrier here. So this fluid here and fluid here is not mixing. Clear? Hello? Make sense? So this is not the only arrangement. You can have 1-4 shell and tube heat exchanger. You can have 1-6 shell and tube heat exchanger. You can have 2-4 shell and tube heat exchanger. You can have 2-6 shell and tube heat exchanger. Okay, is it clear?
Yes, sir.
So multiple possibilities are there. One possibility I am showing you here, but there are multiple possibilities are there. Okay, is my slides visible to everyone?
The bigger the difference between like 2, 6 and all kind of that, they will be only useful in the case when there is much temperature difference between the two fluids.
No.
Or
not at all. When you are using the multiple passes, your heat exchanger become compact. Size of your heat exchanger becomes compact. So whenever you have a limitation of space, you go for multiple passes. But the disadvantage with that arrangement is your pressure drop is going to increase. Clear? Does it make sense? Still not?
yes, sir.
We will come back to that point. So let's say if you are moving from 1-1 shell and tube heat exchanger, if you are moving from 1-1, okay, if you are having 1-1 shell and tube heat exchanger, and if you extend that to 1-4, what different property change is velocity, pressure drop, heat transfer coefficient, length of the heat exchanger. These are the different things which changes. Friction factor. These are the different things changes. Okay, we will see the details on this as we go ahead. Okay, but your question is valid, very, very valid, very much valid. Okay. So one heat exchanger is used when you do not have a space constant. So in that case, you can have a much longer length heat exchanger, isn't it? But if your space is limited, you don't want to increase the length, isn't it? Here you are what you are doing. You are spiraling these tubes in a way, isn't it? Yes or no?
Yes, sir.
So by doing the spiraling of these tubes, what you are actually achieving? You are achieving your length of the heat exchanger becomes small. That means you can make your heat exchanger more compact. In the industry, sometimes the space is a constant, isn't it? So there you wanted to have a compact heat exchanger, but then if you are having the compact heat exchanger, what happens is heat transfer coefficient is going to increase because of that, because your tube side fluid is following a tortuous path, and because of that turbulence will be there, and the heat transfer coefficient will increase. But at the same time, there will be more friction factor, frictional loss, there will be more pressure drop, isn't it? So other things mess up. Is it clear to everyone? Makes sense to everyone?
Yes, sir.
Okay. So this is just a, the diagram which shows what are the different parts present in the shell and tube heat exchanger. Why we are giving more detail here? Because shell and tube heat exchanger is something which you will see in every process industry. Every process industry. You go in any process plant, you will be able to see shell and tube heat exchanger. So these are the different parts named here. So you can see this particular type of end is called as a bonnet type of head, stationary bonnet head. This is a flange which is which is connecting, which is keeping this disc together with this bonnet. Okay, this is a circular disc is there. This circular disc basically keeps, this circular disc is called as a tube sheet, which basically fixes the tubes inside. Then this is the shell. These are the baffles. These are the baffles which basically makes that the shell side fluid will follow a tortuous path, and because of that the turbulence will increase and heat transfer coefficient increases. Also, the spacing between these baffles can be increased, decreased using these baffle spacers or a tie rod. There is a joint is there. This joint is used because sometimes what happens is the temperature is increases, and because of that the tubes, this expansion of these tubes and the shell will not be even. So tube will expand with a different rate and the shell will expand with a different rate, and because of that shell expansion joint is given here. Okay, so that otherwise what will happen, the tubes are going to bend, isn't it? This is a shell side fluid in, this is a shell side fluid out. Then this is the tube side fluid in, this is the tube side fluid out. Then unlike this bonnet type head, there is a channel type of head, because here you can see that fluid is moving through a channel. So there is no partition here, but here is a partition. So this type of head is called as a channel type head. Again, this stationary channel type head is covered by this channel cover here. What is remaining? Okay. Okay, so this again, this partition plate is there which avoid the mixing of the inlet fluid and the outlet fluid. Okay, so these are the different parts. All these parts are, more details on these are given in the book. Okay, so you can look at each of these parts, their material of construction, what type of, things one should keep in mind when you are designing the shell and tube heat exchanger. Everything is there in the book. Is it clear? These are just the supports.
This will come in examination or just like.
So see, in heat transfer, we are not doing everything for the sake of examination. That's not the point. Here we are, see, our aim is not to score more in the examination. Our aim is to appreciate the concept, so that when you go to the industry, you should be familiar with what you are, all these equipments, isn't it? So whether this will come in the examination, I am not saying anything on that. But what I am saying here is, we are doing this because we should appreciate the concept.
Like how can it be included? It cannot be even included in examination. No such
Why not?
thing can be
I can give this figure and I can ask you what is the different parts name.
Sir, that would be too much. It would require so much mugging up.
So nothing I am excluding. Okay, the point is whether I will ask or not. That's a different question. But what I'm trying to say here is
Sir,
don't
it is
look
a
at everything in the
request that you please
examination
don't
point.
ask. Sir, it is a request that you please don't ask because otherwise, like it will be too hard to learn all these.
Don't. What I'm trying to say is, don't study this subject from the examination point of view. That defeats the purpose. Purpose of this subject is not the examination. See, I always say, those who have got very good marks and those who have not got good marks, for me, all of you are equal. Some of you have got good marks because you have done it, carefully. You have done it, sincerity, hard work, and other things. Those who have not got good marks, it's not because they are not intelligent. They are intelligent, but they are not interested sometimes. They are doing something else. Okay, that is the reason. So what I'm saying is, don't look at things in an examination point of view. Look at it in terms of the concept point of view. Okay, when you go to the industry, I don't want you to say to your boss that you don't know cell and tube heat exchanger. You don't know how it is made. What are the different parts in that? I don't want you to say that, isn't it? Because that not only puts a question on me, it puts a question on everyone, isn't it? I have not trained you well. That's what it means. Okay. Got the point?
Yes, sir.
And everything is open book, guys. Why to worry? I am not asking you to mug up. I am not asking you to remember anything, isn't it? Everything is
Yeah,
open.
sir, that would make sense. Now everybody would answer that.
Okay, all right. So all these things, this figure I have made it, but everything is this figure is not copied from anyone. This is made newly made. All the figures in this entire presentation, you can see these are the made by me in order to avoid the copyright and other things. So nothing in these slides is copied from any source. These are made. These are made from the scratch. But this figure is nearly the same whatever is there in the book. Okay. All right, can we move? So already the time is over. Okay. So just before we conclude the today's class, what I'm trying to say is we will have a quiz on Sunday. We will have a quiz on Sunday from 9:30 to 10:30. I have sent the request to the timetable in charge, but I'm not sure whether that is approved or not. Once that is approved, then I will confirm it. Okay. Right now that confirmation I am yet to receive. Why Sunday instead of Monday? Because Monday there was a clash between the first year classes, so they have rejected our request. Okay, but Monday we will have a class. Monday we will have a regular class, and let's hope that we get the permission on Sunday. Somebody said that the Saturday some clash is occurring. So is it possible to have a class from 9:30 to 11? Is it possible to have a class on Saturday?
So Saturday is, I guess, a scheduled day.
It's a Friday timetable that we are saying, so it is not possible. Hello. If it is not possible from 9:30, can we have an alternative time, maybe in afternoon? I'm okay. Any time which you are comfortable with, I'm okay. But we will have a class on Saturday because so much material is there to cover. It's not because I wanted to ask that in the question paper. No, that is not the reason. Probably I will not include something. I will be more lenient in question papers or something. But I don't want you to be suffered whenever you go to some industry or any. So we will complete the syllabus. Whether it is required to take some extra classes, it is okay. We will complete the syllabus. So can we have in afternoon if it is not possible in the morning? I'm okay with the morning. I'm okay with the afternoon. Any time on Saturday, which is comfortable, whichever is comfortable to you. Anyone?
So around 12, the slots are the classes are over, I believe.
So around 12. So can we have from 2 to 3:30? Can we have the class from 2 to 3:30?
The slot is free.
This slot is free. Himanshi, I'm not able to hear you out.
So I said that the slot is free, but I think we should ask everyone.
2 to 3:30 you are saying, or 9 to?
Yes.
Oh,
Yes,
okay.
2 to 3.
So 2 to 3:30 we will have a class. I will send an email, and I am now somewhat, I feel really bad to send one more email because you all might be kind of, feeling that how much confusion I am creating. I am really sorry because last week was extremely painful for me, but it's okay. That's a different thing. Let's, start with whatever we have left with. So Saturday 2 to 3:30 we will have a class. We might have little bit extended class also the way we had today, so that we can cover everything maybe by Monday or so. Okay, is it okay? Is it okay to everyone? 2 to 3:30 I will send an email. 2 to 3:30 Saturday we will have a class.
So it will be on online, no?
Online class will be online. Only quizzes are going to be offline. Class will be online. Quiz, I'm saying tentatively on Sunday. Tentatively on Sunday, I will confirm today. Okay, so quiz is tentatively from 9:30 to 10:30 in the morning, LH121. I have sent the request. Let's hope that gets approved today. If it gets approved, I will send the email today. Okay, confirmation.
So it's a numerical based Moodle quiz or some theoretical quiz?
No, so offline quiz means you have to write the answers, isn't it? So it doesn't matter. It's offline quiz, it's not online. Please, take this in your, pay the attention on this, that the quiz will be offline. Classes will be online, quiz will be offline. Okay, that's why it is taking time. Otherwise, I would have taken the online quiz on any day, isn't it? Any working days. But I am kind of, determined to take this quiz offline, and there we require the availability of the room, and that availability of the room is not confirming because of clashes with the first year students. Let's hope we get it. Okay.
Sir, one more chapter after this is remaining.
No. So one more chapter is there. After this, one evaporator chapter is there. So that we will take it 1 or 2 classes maximum. So if I get 2 more classes, 2-3 classes, we will complete the entire syllabus. And one class probably I will complete all the tutorials. Okay, so 2-3 tutorials are remaining. So in the next week, 1 tutorial class we will get. So there we will cover 2 tutorials, and 1 or 2 tutorials are remaining. So that we will do it in a regular class. Okay. So everything we will be completing by next week. Next week we will complete everything, including your quiz and everything. Does it make sense? And nothing will be removed. Nothing will be removed in the sense, it's not that we will take only two examinations. As promised, we will have 3 examinations and best 2 will be considered. So no change in the policy what we have announced on the very first day. And I am sincerely apologizing you all. Some of these, delays are happening because of me. I'm extremely sorry, but if I would have had another way to handle things, I would have done. But I'm really sorry. There was no alternative ways. So please help us. Okay. All right.
So do we need to bring laptops on Sunday, like the?
No. So see, as I said that
It's
the quiz will be purely based on the book, open book or open notes. You'll not be able to bring laptop. So no online content, nothing. You can bring the printout of this, whatever we have done so far. Okay. So syllabus of the quiz will be whatever we have covered till earlier classes. Radiation first. Okay. Till that will be the syllabus. So radiation, remember I have put 2 slides. So radiation 2 onwards we will not have. Radiation 2 onwards we will have it in the next quiz. I mean that will be included in the next quiz. Only up to radiation 1 we will be the syllabus. Is it okay?
Sir, means like till 14th, the 14th March.
Yes. Can we stop today?
So today's lecture will also be there, no? The starting part.
Is there any question, Aditya, Himanshi? And thank you so much for joining. I mean, I thought nobody initially when 9:30 I have seen nobody, but suddenly 3-4 people have came. So thank you so much for coming. Okay. So unless some students are there, don't feel from this point onward on Saturday 2 to 3:30. Please inform everyone, and also inform everyone that the quiz is on Sunday tentatively. I have sent so many emails, so I don't really wanted to create some more confusion. Okay, please inform. Okay, thank you so much. Let us stop here. We will continue from this point.
Thank you, sir.
Thank you so much.